Good day, everybody. This is the second class during this course on digital communications. In the first class, we discussed about the syllabus, the topics, and a brief overview of what we have to learn during this process. Today, I propose to discuss about two introductory topics. One is on the electromagnetic spectrum and its uses for the purpose of communications and specifically digital communications, and then I suggest a discussion, again a brief one, on the basic concepts of narrowband signals. This concept is important and the issue will come over and over again during our subsequent discussions. So, in a sense these two topics are somewhat isolated, but they have relevance really for our subsequent topics and understanding. Moreover, as I understand, some of the students have not gone through the first level course on analog communications, so they may find it more interesting and informative. Coming to the electromagnetic spectrum, we know that the electromagnetic spectrum is wide in a sense, okay, and much of it is useful for the purpose of telecommunications. Here I have presented a list, a table showing the various frequency bands, frequency range I am calling. For example, the first one is from 3 kilohertz to 30 kilohertz. Do we use this frequency for the purpose of communication in any practical systems? Any answer? A frequency as low as 3 kilohertz or signal between 3 kilohertz and 30 kilohertz, do we use it for the purpose of communication? Telephone communication, okay, where the signal from the end user goes to the exchange, okay, in the analog form, it is within this frequency band, okay, and the corresponding wavelength is of the order of tens of kilometers, okay, between 100 kilometer and 10 kilometer, and this frequency range is known as the VLF band, very low frequency band. I have listed some transmission media and applications. I will come to that somewhat later. The next frequency band is between 30 kilohertz and 300 kilohertz, which is known as the LF or low frequency band, and naturally the wavelength comes down, it is of the order of a few kilometers. The next frequency band is of much importance, in fact we are familiar already about that, is known as the medium frequency band, MF, okay. The frequency band is between 300 kilohertz and 3 megahertz. Now this boundaries of a particular frequency band that I mentioned here is not a very hard one really, but this gives us some idea about the typical frequency bands. There are exceptions, at least in nomenclature of the various frequency bands in the literature. Medium frequency band is very popular for radio signal broadcasting using AM, though just to remind you, a radio signal broadcasting is not a good example of a telecommunication system because it is primarily a one-way system, okay. We only receive radio signals, we can't communicate back with the studio. The next frequency band is also very important, is between 3 megahertz and 30 megahertz, which is known as the high frequency band. We can note that the wavelength is of the order of few tens of meters. This wavelength is very important, we will see somewhat shortly. And then the next frequency band is known as VHF, V stands for very high frequency band between 30 megahertz and 300 megahertz. The wavelength is of the order of a few meters. The still higher frequency band, it increases in decades, okay, it is between 300 megahertz and 3 gigahertz. A larger band this time, okay, is known as ultra high frequency band. The wavelength is a few tens of centimeters, between 10 centimeter and 1 meter. Still higher frequency band is also useful even commercially nowadays, which is between 3 gigahertz and 30 gigahertz, is known as a super high frequency band, SHF, and the corresponding wavelength is only of the order of a few centimeters. I have shown some dotted lines over here really because frequency is higher than 30 gigahertz, okay. Scientists are very hopeful that the higher frequency bands may also be used for commercial purposes some days using wireless techniques, unguided techniques, but still it is broadly in the experimental stage right now really. There are already suggestions for using a frequency band around 60 gigahertz and things like that. But then the wavelength is of the order of a few centimeters or even less than that, a few millimeters. So, in general the higher frequency band is also sometimes known as a millimeter wave band millimeter wave band or microwave band. In fact, any frequency greater than 1 gigahertz is loosely also called as a microwave band. So, the last two bands can also be called as the higher UHF and this SHF bands are also microwave bands. And then we have a very important band somewhat later, where the frequency bandwidth is somewhat narrow between 10 to the power 4 hertz and 10 to the power 14 and 10 to the power 15 hertz, and the corresponding wavelength is about 1 micrometer, very small one, okay, 1000 nanometer typically. Okay, that frequency band is very popular for transmitting signals and receiving using optical fiber cables, OFC. Okay, and within this frequency band, there are smaller segments like infrared, visible frequency band as well as ultraviolet one. Now, coming to the various transmission media, what we are primarily interested here is to have a rough idea about the kind of transmission media or medium which can be used over a particular frequency band. What we see is that there is no one-to-one relationship between a particular frequency band and the corresponding transmission medium that can be used. Okay, like wire lines, simple copper wires, a pair of them as you have seen, okay, can be useful for transmitting signals in the very low frequency band as well as in the low frequency band, and even in some cases over a short distance in the medium frequency range. Okay, which broadly means that you can think of using copper wire for transmitting signals while the signal is of the order of a few hundreds of kilohertz or even 1 or 2 megahertz really. Okay. Similarly, the subsequent transmission medium for the low frequency band, medium frequency band may also be some kind of ground wave transmission. Okay. Now, any transmission medium of this type like ground wave or sky wave, they are also known as unguided transmission medium, where the signal is fundamentally radiated and the signal can go in all directions, and a portion of the transmitted signal will be received somewhere by the receiving antenna. Okay. Compared to that, the other transmission media like wire line, like coaxial cables and like OFC optical fiber cables, they should be called as guided transmission medium, because here we are guiding the signal and the energy associated with that through a medium which is very directed kind of thing, which is firmly connected between the transmitter and the receiver. Okay. Yeah. Ground wave transmission means you can transmit a signal with a large size antenna. The antenna size is roughly related to the wavelength. If the wavelength of the signal is higher, the antenna size, physical size is higher. Okay. So, with a large size antenna, you can transmit the signal where the signal may propagate by along the surface of the earth really. Okay. And earth surface, I do not know how you characterize it. So far as electromagnetic signal is concerned, it is not a perfect absorber of the electromagnetic signal, it is not also a perfect reflector really. Okay, it is somewhere in between. So, it helps in transmission of the electromagnetic signal really, especially when the signal frequency is rather small. Okay. So, you may transmit a signal along the horizon maybe, and this concept is also valid even at a higher frequency up to 400 megahertz really, wherein you can, the signal basically traverses the surface of the ground and covers a large physical distance, and you may get the signal at the other end really. Okay.
So, that wave-guided?
Waveguide is another example of a, guided transmission medium. Okay, is of special type really, which is very useful at higher frequencies of the order of few gigahertz really. Okay, that is a guided transmission medium. Okay, it waveguides. Waveguide itself is a guide which guides the electromagnetic signal, okay, through multiple reflections along a particular structure. The structure may be rectangular in the cross section, okay, or it may be helical, or it may be circular in some cases really. The signal gets reflected from the boundary walls and it propagates. In fact, in a sense, and very common optical fiber cable as we see nowadays is also an example of an optical wave, is an example of an waveguide, where if the signal gets reflected and ultimately it propagates along the guide really. So, waveguides are very useful at high frequencies, but usually over a shorter distance, from a few centimeter to a few meters, okay, or a few tens of meters at the most, for carrying a very high frequency signal. Okay. Now, by sky wave what I mean is the signal we transmit upward okay, and we know that there is an ionosphere in the upper layer of the atmosphere, which is fundamentally filled up with charged ions, charged particles, okay. And the signal that we transmit, you can see that the sky wave is very popular in the HF frequency band, high frequency band really, okay. We transmit the signal upward and the signal effectively gets reflected by that charged particles in the ionosphere, and they come back towards the surface of the earth. So, by making use of reflection from ionosphere, we can cover a large physical distance. Okay, that is the basic principle of sky wave transmission. Okay. And interestingly, this sky wave propagation is typically limited to about 30 megahertz. When the signal frequency is even higher, say in the VHF band, very high frequency band, the signal penetrates these ionospheric particles really, and they go upper in the atmosphere. And that is the fundamental reason why for satellite communications, if any of you have read articles about satellite communications, the satellite communications, for satellite communications, you cannot use any frequency less than 30 megahertz. That is one reason, of course. There are other reasons why. Still higher frequencies are normally found suitable for satellite communications. The usual frequency band, which is popular for communications, telecommunications and all kinds of communications using a satellite, is in the range of UHF and higher frequency bands. Okay. HF or lower frequency bands like medium frequency, low frequency, they are simply ruled out because they can't penetrate the ionospheric layer. Okay. So, the frequency has to be VHF or higher really. In earlier experiments, some VHF frequencies were used for satellite communications, but now it is upper UHF and SHF, the frequency, two popular frequency bands which are used for satellite communications. There are issues of attenuation during the atmosphere and other issues, which ultimately results in the few frequency bands which are popular for satellite communications. Okay. The VHF frequency band is quite okay in the sense that you get about 270 megahertz bandwidth, pretty wide compared to the lower frequency bands, okay. And this frequency band is largely used for televisions, VHF TV as you see nowadays, okay. This is also used for broadcasting using FM, frequency modulation scheme. In fact, you may be knowing, those of you who have attended the subject on analog communications should know that the usual frequency band which is allocated for frequency FM broadcasting is between 88 megahertz and 108 megahertz. Okay. That whole span of 20 megahertz is then divided, subdivided, and for each transmission you effectively get a bandwidth of about 200 kilohertz. So, VHF band is popular for TV signal transmission, FM broadcasting, as well as for some mobile communications. Now, you can see that as a transmission medium, we can have a wireless link that I have not noted here really. We can have wireless medium as a transmission medium. I have not noted it directly like that, in a point to point manner really. You can transmit a signal from one transmitting antenna and the signal will traverse a distance of the order of 50-60 kilometers before the curvature of the earth comes into picture and obstructs the signal really. Okay. And you can have another tower in between, so that the transmitted signal is received by that, and if necessary you can repeat the signal further, and that is how you can have a microwave repeater signal, I mean microwave or VHF, UHF repeater system, whereby the signal can be transmitted in an unguided fashion. Okay. In fact, that kind of system was very popular about 10-15 years back. Now things have changed fast really. There are better mechanisms, more, I mean there are different transmission systems where this kind of signal repetition, especially carrying TV signal, is not very common nowadays really. We have alternative mechanisms of satellite and other transmission mechanism. But when the TV signal or TV broadcasting started in the country way back in late 70s and 80s really, the actual long distance transmission used to take place through this kind of repeater systems really. Yeah, please.
Why it is not possible gigahertz transmission coaxial cable?
It is possible. In fact, the gigahertz, you mean this, you mean coaxial cable or waveguide?
Coaxial cable.
Coaxial cable, yeah. I have some justification sometime later really. I will give you some idea about the attenuation really. What we will find is that the attenuation increases over long distance.
If cable is manufactured properly, the capacity inductance,
Right.
is it possible?
It is theoretically possible, but the cost will be prohibitively large. Okay, and you have other alternatives, so you go for the alternatives.
Because waveguides are very costly now.
Waveguides are very costly, and as I said, waveguides are not normally avoided for carrying signal over a large distance. Okay, the length of the waveguide should be limited to a few tens of meters at the moment. That itself is very costly. Okay. So, if your question is about how to transmit very high frequency signal over a large distance, I have some different answers really. Okay. In fact, transmitting very high signals over a large distance, if the distance is fairly large of the order of few tens of kilometers, then the only suggestion is optical fiber cable. Okay. Otherwise, the signal may be like as it is done in some experimental satellites. Okay. You can use a satellite for transmitting signals over a large distance. Okay. Because at a higher frequency band, even at 27, 30 gigahertz, even at 60 gigahertz, as I said, really there are frequency bands available which is sufficient for transmitting signals. Okay. Only thing is that your transmit signal from the ground station will be somewhat high, because the attenuation there is quite considerable compared to a lower frequency of 4 to 6 gigahertz. Okay. So, with some higher transmission power, a preferred mechanism for covering large distance at a very high frequency of few tens of gigahertz would be satellite, if you are not selecting optical fiber link. Okay. So, that is the engineering decision. You take a decision depending on which transmission medium is most suitable in terms of overall cost. So, when you bring the cost factor into picture, really though there are multiple options, you will choose only one of them. So, waveguides are very popular for short connections. For example, if you have an antenna on at the rooftop and your communication receiver is located somewhere inside a room, then that connectivity may be through a waveguide. If not, if coaxial cable is not suitable there. Okay. And for connecting other very high frequency devices, amplifiers and oscillators and other devices. Well, so this VHF frequency band is actually crowded for and is actually allocated for transmitting TV signals. Some early mobile communication systems did operate in this VHF frequency band around 450 megahertz and even less than 300 megahertz, around 200 megahertz, 220 megahertz. But then, as we already know, this for mobile operations and cell phone operations nowadays, the preferred frequency band is in the UHF band really. At around 900 megahertz, you have a very popular band on which GSM is working, and at higher frequency bands even beyond 3 gigahertz in the SHF band. Okay. Applications, typical applications, I mean the low frequency is very popular for aeronautical applications. This high frequency is popular for citizens band radio, CB radio or ham as we call them really. Okay. It is very popular there. This is also used for the purpose of policing communication through wireless sets, walkie-talkies. Then the UHF frequency band, TV being a major commodity for transmission and reception, TV for transmitting TV signal, part of VHF has been allocated, part of UHF has also been allocated, and then in addition to TV transmission, some satellites also use UHF. Okay, for at least for the purpose of telemetering, telecommand and other applications and mobile communications. These are the major applications. In the super high frequency band, that is between 3 gigahertz and 30 gigahertz, major application is through satellites, okay, for the purpose of carrying TV signals as well as carrying telephone signals and other kind of data. Then at this high frequency, there are certain frequency bands which are now becoming very popular for the local area network, wireless LAN applications. Okay, have you heard of wireless LAN? Okay, and there are LAN standards at around 5.5 gigahertz and higher frequency bands. Optical fiber cable is a major competitor, I can say, okay, and is a clear winner in many applications to wireless communications. Okay, so optical fiber communication cables has got tremendous applications and potential still, and broadly I can say that the major applications are for broadbanding. When you have broadband signals which itself requires a larger bandwidth, okay, it may be wise to think of optical fiber links for transmitting and receiving the signal. Any question at this point? Okay. Then I would now like to briefly discuss about the associated bandwidth that you can expect. So here I have selected some carrier frequencies. Now I am focusing mostly on wireless kind of communication systems. Okay. In fact, in our discussion we will not discuss much about the techniques for transmitting and receiving signals through optical fiber cables. That is a separate subject altogether and will may be taken up in a higher level course, not in this introductory course. We will be focusing mostly on theories and techniques which can be applied to primarily wireless communication systems, and for that reason I have chosen some carrier frequencies. Carriers are well known, okay. They carry some message or signal. Okay. For analog communication system, the signal is analog. For digital communication system, the basic signal may be analog, may be digital. We process them in such a manner that this signal ultimately is converted in the form of information, as I will explain later in detail, and then this information is carried, but fundamentally again through sinusoid carriers. Okay. Like the usual carriers that we select for AM amplitude modulated signal is a sinusoid. Similarly, for most of the cases in digital communications, we select some sinusoids as carriers, and I am talking about the frequency of those sinusoid carriers here. So, I have listed some carrier frequencies, say as low as 100 kilohertz, then 5 megahertz. These are some typical values, not as per any standard. Then 100 megahertz, 5 gigahertz, and even in the optical one I have taken here as an example to bring in the issue of bandwidth. And then we can see that a carrier of 100 kilohertz may be used primarily in the low frequency band. Okay. And then for long wave radio, and then the typical bandwidth that you can expect in that low frequency band is of the order of a few kilohertz only. When the carrier is 100 kilohertz, I mean, can you think of transmitting a signal or message whose bandwidth is itself say 200 kilohertz or even say 120 kilohertz? No, we do not do that really. Okay. That is the meaning, significance of carrier is lost in that case. Okay. So, for if we are choosing a carrier in the low frequency band which is of 100 kilohertz, the kind of bandwidth, okay, which is very important parameter for the basic signal that can be conveyed, that can be transmitted over this carrier frequency is limited to a few kilohertz. Whereas, when you go to the higher frequency say at HF in the short wave mode and with a typical carrier frequency of 5 megahertz, we can get a bandwidth of 100 kilohertz, okay, or even more in some cases. Okay. If I go higher up in the very high frequency band, we can see the very high frequency band is from 30 megahertz to 300 megahertz. Okay. One can use a carrier frequency of 100 megahertz there, okay. And then one can easily get a bandwidth of a few megahertz, even up to 5 megahertz. Okay. Smaller bandwidth can be taken care of, but too small a bandwidth again is a problem. Just if you are using a carrier frequency of 100 megahertz and if you are trying to transmit a signal whose bandwidth is 1 kilohertz, theoretically it is possible, but practically it is going to be again difficult really. Okay. Whereas, when I am choosing a carrier frequency of 100 megahertz, we should not think of transmitting a signal with a very high bandwidth of the order of 40-50 megahertz. Okay. So, somewhere in between we have to select the bandwidth, or if we know the signal bandwidth, we have to select the carrier frequency appropriately. So, the pointer is towards understanding and analyzing the bandwidth of the basic signal which we are thinking of transmitting or receiving. Okay. And depending on the bandwidth of the signal, we should pick up the appropriate carrier frequency over a given particular frequency band. So, if I have a very high bandwidth signal, then it may be wise to consider a higher frequency band, say I am saying microwave band at a frequency of say 5 gigahertz, okay. And then you can have a bandwidth of the order of a few tens of megahertz, say 100 megahertz, okay, or even more. And in the optical frequency band, okay, it is very easy, not at all very difficult, because the technology has developed very nicely over last 2 decades, and it is very easy to get a bandwidth of the order of a few tens of gigahertz, stretching, people are saying, up to maybe a few terahertz really. Okay. So, my point here is to show that 2 things. One is, you must know the bandwidth that will be necessary, the bandwidth occupied by the signal, or the bandwidth that will be necessary for transmission of this signal. Okay. If you have a larger bandwidth signal, you should think of higher frequency as carrier. Okay. If the bandwidth is lower, then think if you are allowed to transmit at a lower carrier frequency, choose that. If you are not, then take care of the signal processing necessary and go for the allowed frequency band, which may be somewhat higher than necessary. Okay. And if you have a very high frequency band signal, then better option would be to go for optical fiber communications. The actual transmission medium which can be selected is decided by several factors. A very important of them is the loss, transmission loss. Okay. And by transmission loss, here I mean the power loss. A popular unit for describing that is dB per kilometer. dB stands for decibel. Okay. Like if you have chosen a twisted wire, okay, twisted wires they come in various standard wire gauges. Okay, typically at 16 American wire gauge, okay, AWG. The other unit, popular unit is that of SWG, standard wire gauge. Okay, 16 AWG means a bit thicker one. Lower the AWG value, thicker is that wire really. So for that twisted wire, if you are operating the twisted wire, using the twisted wire at a typical frequency, by this typical frequency I mean in case you are using a carrier, in some cases the carrier frequency or some middle frequency of the signal bandwidth. Okay. If that is of the order of 1 kilohertz, we can see that the power loss is 0.05 dB per kilometer. What does it mean? It means that transmitting a signal of the order of a few kilohertz through a somewhat thick copper wire is very easy. The signal is not much attenuated because it is a copper wire, the resistivity is very small, okay, and the frequency being very small, there is hardly any capacitance, distributed capacitance, etc., and the signal travels very nicely. There is hardly any loss, resistive loss in the signal, and you can use the copper wire over a large distance, like typically from your house, from the telephone instrument, the exchange may be located about a few, say 5, 7, 10 kilometers away, and you can stretch the copper wire, okay, and the attenuation is very nominal, rather small really. So you do not go for amplifying your speech signal before you send it through copper wire to the exchange, as simple as that. Whereas the interesting part is, if I think of transmitting a 100 kilohertz signal whose middle frequency is 100 kilohertz, modulated or not, okay, over the same twisted wire, I now see that the power loss is much more, is about 3 dB per kilometer. What does it mean? Pardon? So much of the power is lost really. So I should not think of transmitting a rather high frequency signal through the same twisted wire pair. Okay, the signal will get highly attenuated, and if I have an arrangement for boosting or amplifying the signal or do some more processing of the signal in between, then I should not use that really. Okay, I just leave you to think about the story of submarine cables. Have you heard of submarine cables? Okay, cross continental cables which do exist really. Okay, now which are a bit old, really, a few decades old, that there are cables available, okay, connecting two continents for long distance telecommunication purposes. Okay, those cables are primarily copper cables, okay, and they are used for transmitting telephone signals, multiplexed, several telephone signals multiplexed together, they are transmitted through that really. Okay, so I would leave you to think about how that is possible really. If you have read basics of signals and networks really, if you know about the distributed modeling of a twisted wire pair or parallel wire telephone lines, you can find an answer really. Okay, I mean, then it has also been possible really, but the point remains, the cost of that kind of long distance telephone wireless communication link is pretty high really. So coming back to one of the earlier questions really, yes, whenever it is absolutely necessary, cost is not the issue. Yes, you can go for the technique which is available to you. You can go for the material or the medium which is available to you. Okay, but the same solution will not be accepted everywhere. The same telephone wire, if you like to use for connecting two distant cities, say Calcutta and Delhi, I mean, it may not be so appreciable, especially when there are alternative technologies available. Okay, so one has to think about the possible technologies, ultimately assess the cost of the system, and then select. So the point is, twisted wire pairs, they are good for low frequencies of the order of a few tens of kilohertz. For signals higher than hundreds kilohertz, I mean, things are difficult. One has to think of special precautions really. I will give you one more example. We won't discuss further about that subsequently, but you may have heard of some kind of DSL, digital subscriber loop, okay, which is a somewhat recent system or product which has hit the market. This DSL and various varieties of them really, XDSL in general, they primarily use copper wires, okay, for transmitting signal which supports a data rate DSL has come later, okay. It is ready to accept digital data, ones and zeros, at the rate of a few megabits per second, which is very high. By simple calculation, it can be shown that the spectrum or the bandwidth of the signal is of the order of a few megahertz, okay. But still, that high bandwidth signal is still taken through twisted old copper wire pair, okay, twisted or parallel copper wires, okay, over a distance of a few kilometers, and then it is processed further, and this high frequency signal communication has been possible using twisted wire, but this has been possible using modern techniques of communications there, okay, with involved processing of coding and modulation of the basic signal before it is transmitted through the actual signal, through the actual wire pair. That is an interesting story. Well, coming to coaxial cable, we find that coaxial cables are no good at very low frequency, fundamentally because the size becomes large really, okay, and the cost increases. So, coaxial cables are popular at a higher frequency, and say at 1 centimeter diameter coaxial cable at 3 megahertz may have an attenuation of 4 dB per kilometer, okay, 4 dB per kilometer, which simply means that one should not think of a link over say a distance of 30-40 kilometer by using a coaxial cable, whereas a link of the order of a few kilometers, 1 kilometers or a few kilometers using a coaxial cable does make sense, okay, without amplifying the signal in between. Waveguides, they are good at still higher frequencies, SHF and higher microwave band in general, okay. The typical loss is 1.5 dB per kilometer, okay, at a frequency of 10 gigahertz or even higher frequency band, fine. So, when the frequency is very high, waveguide is the choice. Coaxial cable, yes, can be used, but only over a short distance, otherwise this attenuation is going to increase, the power loss is going to increase tremendously. Optical fiber, as I said, okay. Now, with the present technology, the attenuation is hardly appreciable over 1 kilometer really, it is less than 0.5 dB. People say, I mean, for some high quality optical fiber, the attenuation may be as low as 0.15, 0.2 dB per kilometer, okay. So, this means a point to point communication link, okay, in terms of power loss is not a problem if the distance is even say about 30-40 kilometers. But there are other issues really, when you really think of transmitting high frequency pulses through an optical fiber, there are issues of dispersion, etc. And once those issues are controlled, then nowadays repeater-less or amplifier-less optical links are possible even stretching beyond 30 kilometer. That is a great achievement, and because of that the overall cost of high bit rate communication links have come down drastically over last 2 decades. Well, yes, please. You have some question on this slide? Yes.
Sir, you were saying that for coaxial cable, typical frequencies of 3 megahertz, power loss is 4.0 dB per kilometer.
Per kilometer, okay.
And we work at around 100 megahertz or something.
Yes, you
then
can.
what would be the power loss?
You should not think of a few kilometers of coaxial link in that case.
And that is
Okay. See, this is one typical one, but this is not the best value always. This is not the best value. Okay, I'll give you an example really. I don't know how is your local cable TV network operating in your locality. Do you have any idea whether it's coaxial cable or something else? Okay. Usually it predominantly was coaxial cable till recently. Okay.
RF cable.
Pardon?
RF cable.
What is that RF cable? Huh? Usually that's a kind of coaxial cable. That's a trade name basically. Okay, I mean it's not a technical name. Okay, RF cable means cable which is good for carrying RF signal, radio frequency signal. RF stands for radio frequency. Okay, now essentially that's a coaxial cable. Okay, and by maintaining the quality of the dielectric which comes in between the central conductor and the outer conductor, one can control the power loss as well as the other dispersion in the coaxial cable really, and hence can operate at higher frequencies. For cable TV purposes, the cable is primarily coaxial, it was really, okay, and it operates at a very high frequency band very nicely in the UHF band also mostly with a reasonable attenuation, but within a locality, within a radius of a few kilometers. Okay. So long as the distance is up to a few kilometers, and if you see they do have some amplifiers in between. Okay. So, when you amplify the signal, before the signal is too much distorted, with simple amplifier you can again cover a larger distance. So, ultimately it is the distance which matters at higher frequency. Is that okay? For your information, now your cable networks, I mean, they are switching over to optical fiber links, okay, because the cost of fiber has come down drastically, the quality has improved. Well, I switch over to the next topic of what I call is baseband representation of narrowband signals. This concept is very important, because in the name of modulated signal or signal for transmission reception, in many cases, and at least in most of the cases during this course, we will be discussing about real band pass signals. Signal which can be transmitted, which is a real signal, okay, but essentially the signal is a band pass signal. The idea I have already brought in, because just now I was talking about bandwidth, okay, bandwidth, and now if I think of a modulated signal where the signal is modulated around a carrier frequency, I say the modulated signal is a good example of a band pass signal. Do you accept? Where around the carrier frequency the signal after modulation will appear, so that I can talk about the bandwidth of the modulated signal. Okay. Now, so the whole signal, which is a real signal, I can say is a band pass signal. It is not a low pass signal, and it is not only a high pass signal. Okay. My point is that this kind of real band pass signals can very well be represented by an equivalent baseband form or low pass form. Okay. Though the equivalent low pass form is no more a real quantity, is a complex quantity, but that is not a problem really. We are all familiar with the theory of complex variables and other things. Okay. And there are different advantages if we go for this kind of approach for understanding real band pass signals. Okay. I will talk about them really. So, to start with, let us say that we have a narrow band pass signal. This may be a modulated signal, but need not be a modulated signal. You can think about other kind of band pass signal, okay. And then let me call Fc as the center frequency. If it is a modulated signal with say two nice side bands, as it happens in amplitude modulation, traditional amplitude modulation, Fc may mean the carrier frequency, but again this need not be the carrier frequency always. In general, if Fc is the center frequency of the band pass signal, okay, then I can say that Fc can be expressed as F1, where F1 is the lowest frequency component in that signal, plus F2 minus F1 by 2. Is that okay? Okay, where F2 is the highest frequency component. Okay, that is, so Fc is the middle point, the middle frequency between F1 and F2. Okay. Then traditionally we say that the bandwidth of the signal is F2 minus F1. Okay. Now, there is an intriguing question at this point really. I mean, I am not going to answer that really, but if you are oriented mathematically, you may think about how this bandwidth is defined, how this F2 and F1 are chosen really. Okay. Is it that for the signal we are talking about, the band pass signal we are talking about, there is no signal energy beyond F2 in the higher frequency band and beyond at frequency less than F1? Is it like that? Well, yeah. So he talks about the 3 dB point. Yes. So he says some 95% of energy. Okay. There are multiple views to that really. Okay. And in fact, I mean, there are different definitions and ways of talking about mentioning the bandwidth. Okay. But we are steering clear now. We mean that the signal is essentially band limited between F2 and F1. That means there is no energy component of the signal beyond this range of Fc plus minus Fb by bandwidth by 2. Okay, there is no signal component really. Okay. Now this may usually this is not your 3 dB cutoff frequency. Okay. But this, so your 3 dB cutoff frequency may be somewhat smaller than this bandwidth. Now, for a narrowband signal, we say a signal, a band pass signal as a narrowband one when this bandwidth F2 minus F1 is much smaller compared to Fc, much smaller I say, and as a rule of thumb, though there are exceptions. Rule of thumb, you can say that the ratio of the bandwidth and the carrier frequency, if it is between 1% and 10% of the carrier frequency, then we can say that the signal, the band pass signal, is a narrow band signal. The emphasis is on narrow. Okay. So, what may be the counterpart for narrow band signal or narrow band pass signal? You may very well think about a wide band pass signal, isn't it? A wide band pass signal or wide band signal in general. Okay. In this course, we are not going to focus much on wide band signal and processing of that. Okay. Our focus will be mostly on processing and related theories for narrow band signals. So, I will continue with the narrow band signal, but let me tell you that there are practical systems and examples more and more in recent years of wide band signals and systems, communication systems. There are differences in the theory and their uses for wide band signal and system design. Okay. So, representation of narrow band signals in an equivalent form. I would like to write a general expression for a narrow band pass signal. A narrow band pass signal I am now calling as a narrow band signal. Okay. Xt, let xt be that real narrow band pass signal. Okay. Then I am writing a time domain expression, t stands for time. So, I am writing xt is at cos 2 pi fct plus phi t. Just think a little bit and let me know whether this expression is a pretty general one. If you give me a narrow band pass signal, whether I can write the signal in this form in time domain. I will say yes, if t stretches from minus infinity to plus infinity. Okay. If the signal expression is this only over a very short duration, short range of t, then there may be problems, because you are familiar with Fourier transformation. If I give you a very short duration pulse, you can very well analyze it, okay, and find the Fourier transform and see that there are the spectrum of the signal stretches towards plus minus infinity. So, loosely speaking, narrower the signal duration, okay, and whenever there are sharp changes in the signal in time domain, this implies that there are the signal is rich in high frequency components really. Okay. So, I can say that, but if xt has to be a band pass signal, the signal has to be limited within the bandwidth f2 minus f1. Okay. There cannot be very low frequency, there cannot be very high frequency beyond f2 even. Okay. So, that way this is a general expression, okay, for unlimited, for the full range of t. Okay. Now, tell me briefly what I mean by the negative range of t really. Just now I was telling that xt is a real band pass signal. So, if it is a real band pass signal which you can generate, okay, which you can obtain from a source, real physical source really, then there is no question of t being negative really, is it not? Huh? Okay. Now, xt may be rewritten, I can very well rewrite by expanding this form really, and again cos fc here is a center frequency, not necessarily the carrier frequency. So, on expansion, simple trigonometric expansion, I can write this as at cos phi t into cos 2 pi fct minus at sin phi t into sin 2 pi fct. Okay. And then what I am doing is I am taking out this portion at cos phi t and writing it as uit, and this portion at sin phi t I am separating out and writing it as uqt. Okay. These are two notations. So, that xt is uit cos 2 pi fct minus uqt sin 2 pi fct. Can you guess what is my intention here? I am separating out the portions, leaving only the center frequency component. Okay. And yes, as he says that uit in some context, at least for the modulation demodulation schemes, okay, we call this as an in phase component and uqt as a quadrature phase component, because fundamentally a cos 2 pi fct waveform and a sin 2 pi fct waveform, they are in quadrature, they are orthogonal to each other. Okay. So, this expression now I can also put in this form really. Xt is a real signal, Re for real, of a complex expression inside, okay, u curl t times exponential of j 2 pi fct. It's easy to verify that if I really expand, I get this expression really. Okay. So, I can find that this u curl t is nothing but uit plus j uqt. Okay. So, I call this u curl t as the complex low pass equivalent of xt. U curl t is a complex parameter. It's uit plus j uqt, where uit and uqt in their own merit are real signals. Uit, uqt are real because they are at cos phi t, okay, they are at sin phi t. So, they are real, okay, but u curl t is a complex quantity and is a low pass equivalent, I say. It is a low pass equivalent because I have set aside this multiplying term of cos 2 pi fct and sin 2 pi fct. Okay. Which means that the real bandpass signal xt now I can describe completely by a complex low pass equivalent u curl t and the center frequency fc. Like if you tell me the center frequency of your bandpass signal that you have generated without telling me, and you tell me what is uit and what is uqt, I can show you what your xt was really by using this kind of diagram, isn't it? The previous expression, this expression xt is at cos phi t, this uit cos 2 pi fct minus uqt sin 2 pi fct, I can take, okay, and can put it in this pictorial form, okay, where I have got two multipliers, analog multipliers essentially, and then one adder which is a subtractor, and then if I feed uit here, the one that you have given me, if I feed uqt here, okay, and you have told me the center frequency fc, so I generate a cos waveform from there, and I know this is I can design a pi by 2 phase shifter by which technique? Hilbert transformation. Okay. Okay. Even circuit wise also it is rather easy if you give me a cos component to generate two sinusoids which are orthogonal to each other really, okay, by using passive circuits as well. So, I have generated the sin 2 pi fct here, cos 2 pi fct here, and then I get finally xt. Okay. So, if you give me uit uqt cos 2 pi fct, I can find xt. Okay. So, I can say that now instead of describing the features and theories and usages of xt, if instead I discuss about u curl t knowing fc, then I do the same thing really. Okay. So, the emphasis may be in developing theory in terms of u curl t rather than xt, because both of them have got the same theory which are equally applicable, okay, and for practical implementation also this complex low pass equivalent has got gives us greater insight into the design and building of the systems and subsystems. And there is one more subtle reason why it is very popular, this kind of approach of using complex equivalent representation of a real bandpass signal is that of simulation, especially for digital communication systems. Simulating various principles and theories of digital communications for their usages in practical systems is very popular. So much so that I can say that no well designed digital communication system is first designed in hardware nowadays before its extensive simulation is done elsewhere. Do not try that really. Okay. If you have any plan to design a communication system in hardware, digital communication system which you hope to be very efficient, please go for extensive simulation beforehand. Okay. And when it comes to simulation, okay, it can be done in many ways really. One popular way is to really do the things the way it would happen in the real field. Okay. And for that you may have reason to generate real bandpass signals like xt, etc. You would like to see the modulated signal, okay? And there the problem is, if I really deal with a real bandpass signal which is a narrowband one, then because of the restriction I had put or I suggested that the bandwidth of the signal is very small compared to the carrier frequency. Now, if you take a very simple example of a modulated signal for 1 bit of information, 1 bit means so one high logic high level of say duration 1 second. Say you have a data whose bit rate is 1 bit per second. Okay, you get bits at various rates nowadays. So, let us take a bit sequence or information sequence at 1 bit per second, and then suppose the job is to transmit this using digital communication principles, okay, with a carrier say 100 hertz, 100 times, okay, more or less the bit rate is 1 bit per second. Suppose I choose a carrier of 100 hertz. Now, while simulating, if you want to see the modulated signal following some principle of modulation, one technique may be binary phase shift keying, there are other candidates, but then after whatever modulation you try out, really if you like to see the modulated signal, think that your carrier is going to be presented and it is the information bits which will change the carrier phase or amplitude or frequency, okay. And there the modulated signal, if you want to see for better viewing, for better assessment, etc., you would like to have at least 2 samples per nominal carrier duration, per cycle duration of the carrier. Does it make sense? Okay. I mean, it is something like this. If I have a bit sequence like this, say 1 0 0, and if this is 1 second, then my point is, one simple example may be that following binary phase shift keying, I would like to have a carrier sinusoid with some phase say cos omega ct, cos 2 pi f ct in this duration, so that in the next bit duration, I can change it to represent 0. Now, when I have 100 cycles of the sinusoid over 1 second duration, over 1 bit duration, this is TB, then for viewing and assessment I should have at least 2 samples per cycle duration. Per cycle duration is how much? 1/100th of a second. Over 0.01 second I should have 2 samples, following which theorem? Nyquist sampling theorem, isn't it? And it is better when you do it, you will feel that it is better to have more than 2 samples really. So, you have 2 samples over 0.01 second. So, how many samples you need over this duration? 200 samples for representing 1 bit, isn't it? And then if you are interested in error performance of the whole transmission reception scheme, usually you should test your modulation demodulation schemes for thousands or millions of bits. So, if you think of the total number of samples you have to generate, the number of samples may run into several trillions maybe for statistically reliable assessment of any performance parameter. Okay. Now, if you take my advice and go for equivalent low pass representation even in simulation, okay, you have to deal with at least 100 times less number of samples really, which increases the speed of execution, speed of simulation time, etc., and you get the same information. If you want to see the modulated actual real modulated signal, you can always reconstruct that following this scheme. Okay, so that's a very important reason why complex low pass equivalent description is very important nowadays. Well, I'll hurry through. In terms of spectrum of the signal, okay, the spectrum of the main signal can be expressed like this using Fourier transformation technique, and then I have put the actual signal in terms of its complex low pass equivalent u equal t real of that, and then I make use of this identity that real of a complex quantity is half of the sum of the complex quantity and its conjugate, isn't it? A plus jb and a minus jb, okay, if you add and divide by 2 you get a, the real part, that is it. So, the spectrum, the Fourier transformation of the signal actual xt I can express in this, and the final expression is like this: half of u f minus f c plus u star conjugate of complex conjugate of u minus f c where u of f is nothing but the Fourier transformation of the baseband equivalent signal, which simply means that the spectrum of the original band pass real signal can again be expressed in terms of, if I know the Fourier transformation of the complex low pass equivalent signal. So, again in terms of spectrum I do not lose anything really. Pictorially the situation is like this. If this is the spectrum, magnitude spectrum of the real band pass signal centered around frequency fc stretching up to fc plus minus w by 2, where w indicates the bandwidth. Okay. Then this is the positive spectrum on the positive frequency side, this is on the negative frequency side. If this is the spectrum, magnitude spectrum for the original band pass signal, then the spectrum for the equivalent baseband magnitude spectrum is going to look like this. It's now limited between plus minus w by 2 around 0. Okay, and you note see the height of the spectrum has increased, has doubled basically. Okay, this shows that u curl t essentially is a low frequency signal or low pass signal. Okay, so the in terms of spectrum also, if I know the spectrum of the original signal, I can construct the spectrum, magnitude spectrum of the baseband signal, or if I know this and the associated phase spectrum, I can reconstruct the spectrum of the original signal. Okay, so we don't lose any details in that really. One last point is that of the energy. Okay, energy of the original signal and energy of the equivalent low pass signal. With a little bit of approximation, we can see that if I know the energy of the equivalent baseband signal, I know the energy of the original signal and vice versa. For that, I am computing the energy for the signal. Okay, simple expression, integration of the signal as long as it exists. Okay, so in the limit minus infinity to plus infinity x square t dt. The same thing with straight away expansion using the identity of the complex number, as I noted earlier, can be put in these two forms, where the first term does not have any component of cos 2 pi f c t or omega c t. Okay, this portion is because of the complex low pass equivalent portion, whereas the second term involves both. Okay, and the very interesting point is that the energy of the original signal x t is approximately the first term, not the second term. Can anybody quickly guess? The second term reads half of integration of mod u curl square cos 4 pi f c t, twice the frequency of the original signal, plus twice of phi t, phi was the initial phase variation, dt. Okay, can anybody guess why this term is not significant compared to this term? Integrated, and the integrand involves a cosine wave form. Okay, and just now we saw that ut is a low frequency signal. That means variation of ut, the complex equivalent, over one cycle duration of the carrier is very small, and as a result I can say this is approximately this term, second term, integration of cos 2 pi f c 4 pi f c t, which will over a large integration time will almost be very close to 0 really. The situation is something like this. Okay, see this envelope is dictated by the complex low pass equivalent. These are the actual modulated signal, the second part really. Okay, now if you integrate this kind of sine wave, the essentially sine wave with small changes in phase, small changes in amplitude, small change in phase is because of 2 phi t, small change in amplitude is because of u curl t, okay, magnitude, and then I can say that summation of this part will be very close to 0. What will stand out is the first component basically, which means energy of x t is almost equal to the first part, which is nothing but the energy of the complex equivalent signal. So I could say that the energy of the signal is approximately very closely the energy of the complex equivalent signal. The spectrum of the original signal is very uniquely related to the spectrum of the complex equivalent signal, though I showed the magnitude response here, and I showed that in terms of representation also they are identical, which means it make good sense to study the theory of signal processing so far as digital communication is concerned in terms of its complex equivalent, low pass equivalent, rather than the actual real band pass signal. Any quick question? We are running out of time. Any quick question here?